Okay, welcome back. This is lecture 6, Machine Learning from Data. And in this lecture, we will talk about bounding the growth function. Okay, if you remember what the growth function was, this was a new measure of complexity of a given hypothesis set that views this complexity through the perspective of a data set, right? So in this lecture, we will focus on bounding that growth function, which was denoted by m sub h of n, right? And then we'll go into a further detailed sort of analysis of if we can bind or bound the growth function by some value and how to do that. So that's the major focus of today's lecture. And let us begin by kind of putting everything together, what we learned until now. Okay. Now, the growth function, which is of course denoted by m sub h of n, if you remember, it reduces the infinite number of hypotheses to a finite set of dichotomies, right? Now, in this lecture, we will begin to analyze that. If you remember, and let me quickly show you, we saw this example, very small example, in which we had a data set where we had positive points, and then let's say these were negative points, right? And then we figured that we can have any number of many, I would say not any, but many hypotheses that actually can separate this data, right? And all of them are valid. So basically we understood that there is just one function that can implement this, or maybe that can separate the data here. So this is what viewing a hypothesis through the lens or through the perspective of a data set means, right? I'm not looking at this hypothesis set in isolation. I have to view this with respect to the data I'm working with, and that helps me in a way. Right? That helped me figure out the deficiency in my hypothesis set, which kind of made things easier for me because I don't have to go and look for every possible hypothesis, right? Which was infinite. And then I don't have to go and look at that, and we found that in the previous lecture. So what this growth function, going back to the growth function, what this growth function did was that it considered the worst possible x1 up to xn, basically n data points, and found the number of dichotomies that could have been implemented by this hypothesis H. Basically what we did was pick endpoints, implement all dichotomies that are possible on that particular endpoints, right? And that will tell us how diverse my H is, right? How many dichotomies can I implement, right? And next I can maximize that. That's why this max comes in, right? I will maximize that over all data sets of size n, right? We even looked at the perceptron example, if you remember. We said that the dichotomies that can be implemented with a peculiar data set where we had everything in a single line, right? That in with 3 we were not able to implement this with a perceptron, with this one being positive and this being negative. But then there was a way out to kind of implement a perceptron with 3 points, right? So we were looking at all possible set of 3 points, and then we went ahead and looked at all possible 4 points. And that's what this maximization is talking about, right? Maximize over all data sets of size n, and then the maximum number of dichotomies that can be implemented by a hypothesis set H as viewed through the lens of a data set is my growth function, right? So that's what we discovered, or that's what we established in the previous lecture. Okay, so what are we going to do in this lecture? In this lecture, we are going to try to answer 2 questions. Number 1, which is really important, and we kind of started talking about it even in the previous lecture. Can we bound m sub h of n by a polynomial in n? Okay, so this is the first question that we are trying to answer in this lecture, by a polynomial in n. And then the second question that we're trying to answer, which goes back to where this all started, and that was the error bar, right? So now the second question, which is obviously very important for us, is can we replace the cardinality of all possible hypotheses by my growth function? Because now I'm really close. I can tell, right, that I'm really close. So can I replace this by my growth function in the generalization bound? in the error bar, because that's what we want, right? So in the generalization bound, or in other words, the second question actually means, is the bound useful in terms of the error bar? Okay, so in the previous lecture, we saw that this growth function helps us figure out deficiencies in the hypothesis set. For example, and let me quickly remind you, in the perceptron model, we saw that at n, I think it was n equals 4, right? All dichotomies couldn't be implemented. So n, by theoretically, it should have been like 16 dichotomies, 2 to the 4, but we could just implement 14, right? So we did see that there is a deficiency that exists, and there are ways to figure that out. And then the second hypothesis set was the one-dimensional positive ray. And what we found out about it is that this hypothesis set implemented 3 dichotomies at n equals 2, right? So n equals 2 should have made like 4 possible. 2 to the 2 is 4, but actually we were able to implement one less, which is 3, right? So it became, think about this hypothesis set as becoming deficient so early. In fact, it just became deficient at n equals 2, which was great, right? That's good news for us. And then there was this 2-dimensional rectangle, right, that I think became deficient at n equals 5. Yeah, n equals 5. So basically what we found out was that whatever m sub h of 5 was, obviously we cannot implement all 2 to the 5. Right, this was the basic thing that we're trying to get at, which kind of tells us m sub h of n drops below 2 to the n, right? So the key takeaway is that m sub h of n, which is my growth function, drops below this theoretical 2 to the n. That's great. That means there is hope. And then eventually, which is like another important aspect of finding this deficiency, was the breakpoint, because the breakpoint actually helped us reveal that deficiency, right? So we defined a breakpoint as any k, or maybe a breakpoint is any k for which my m sub h of k is strictly less than 2 to the k, right? So this is the point that helped, this is like a quantity that helped me reveal the deficiency in my hypothesis set. Okay, so having put these things in perspective, before even trying to figure out a bound for my growth function, what we are going to look at is a closer relationship between my growth function and breakpoint using a few short quizzes, because that is going to help us understand this relationship better. So the first quiz that we're looking at is that I give you a set of k star points, x1, x2, and so on up to xk star, on which h, which is like a hypothesis set, implements less than 2 to the k star dichotomies. Okay, so the options are, and you have to obviously pick one or more options, whichever is applicable. The first one is k star is a breakpoint, k star is not a breakpoint, all breakpoints are greater than k star, all breakpoints are less than k star, and E is we don't know anything about breakpoints. Okay, if you think about this, this is like a specific set of k star, right? Points that are given to us. So if you're thinking the correct answer to this question is E, then you are right, because in order to prove that k star is a breakpoint, we need to show that my H, the hypothesis set, cannot shatter any data set of k star points, and not just like this specific one, right? So that's the hidden sort of message going on there, that I'm giving you that particular set. But if you remember, I have to prove for any data set of k star. So you must show that your data set is deficient no matter what set of points, which is why the answer to that question is E. Okay, so that was quiz number 1. Let us move on to quiz number 2. Okay, for every set of k star points, now notice this is different. For every set of k star points, x1, x2, and so on up to xk star, H implements less than 2 to the k star dichotomies. Okay, So what do you think the answer to this question is? K star is a breakpoint. So because my hypothesis has become like whatever dichotomy it's implementing is less than my theoretical to the K star, and this is for every set of K star points. So this I think fulfills my definition of the breakpoint, right? So definitely A is true, but let's look at other options as well, because it might be that there is something that's included. And okay, so K star is not a breakpoint. This is obviously not true. B is not true, right? Because we just said that this is the definition of a breakpoint. C, all K, that means all points that are greater than or equal to K star are breakpoints. Well, this is to a large extent true, because if we cannot shatter K star points, we cannot shatter anything greater than that, right? So I would go with A and C, right? Because this is also true. When you could prove that K star points cannot be shattered, anything greater than that could also be not shattered. D is the complete opposite, so that's not correct. And E, of course, we know because the definition was correct, so that's not correct. And that finishes quiz number 2. Okay, let's move on. Quiz number 3, to show that K is not a breakpoint for H, and just like reminding you, K is the one that reveals the deficiency in H, right? So we have to show here that K is not a breakpoint for H, and these are the given options. Let's see what options are applicable. So even before looking at the options, if you think about the breakpoint, to show that K is not a breakpoint for H, we have this liberty to pick a set of K points, right? So if we can show that a set of K points, x1 up to xk, which can actually shatter H, or which H can shatter rather, right? So H shatters a data set, right? And it could be like a certain set of points, like which is x1, x2, and so on up to xk. So if this is possible, then I've shown that H can implement this dichotomy for a given data set of size k, and so k is definitely not a breakpoint. So I think A has to be the correct answer for this one. Let's keep looking because we might find some extra information. Okay. B, show that H can shatter any set of k points. Well, this is technically correct, right? Because it should be applicable to any set of k points, but I think it's an overkill, because if you remember what we said, that like in the perceptron example, with 3-point example, if you remember, right? We took that very peculiar like 3 points, right? Plus, minus, plus, and we said that H, like my perceptron cannot shatter this, of course, but then there are other set of like 3 points which the perceptron can shatter, right? So there was no kind of uh, need to like just like keep going and getting every set in the inverse setting. So this is the inverse setting where we are showing that K is not a breakpoint, right? So it is enough to just like show that this like perceptron works for these 3 points, whatever these points are, right? And that's enough, that this like 3 is not a breakpoint, at least for a perceptron. So this can be true, I would say, but this is like an overkill is what I'm saying. Okay. C, show a set of K points which cannot shatter. Okay, so this is like going in the opposite direction. We're not interested. Show H cannot shatter any. So again, going in the opposite direction, we can simply discard that. Show M sub H of K equals 2 to the K. Okay, so if the growth function is equal to my theoretical value, which is 2 to the K, that means we can shatter K points. So I think this is also correct. So for this quiz, the correct answer is A and E, right? This is also correct. This is indirectly saying the same thing as in A, right? So this is like similar to what we said in A, but this is also correct. So similar to part A. Okay, so that was quiz number 3, and then let's look at quiz number 4. Now this is the opposite. We have to show that K is a breakpoint for H, right? So let's look at that. What is the definition of a breakpoint? It reveals the deficiency in my hypothesis set. So now we have to show that K is a breakpoint. Okay, let's see. Show a set of K points, x1 up to xk, which H can shatter. Well, remember now we are trying to prove that K is a breakpoint, and in order to prove that this is a breakpoint, as we said in I think one of the earlier quiz questions, right? we have to show that it has to shatter like any set of k points and not just like one. So I would discard A. Let's move on to B. Show H can shatter. Okay, and first of all, like even without looking at that, I'm trying to show that K is a breakpoint. So this can shatter is actually going in the opposite direction, right? To be very simple, I can just like discard them quickly. Okay. Show a set of k points x1 up to xk which cannot shatter, so it's going in the right direction, but then it's a set of k points. I don't want to restrict myself to one set. Again, going back to the perceptron example, I did show that for 3 points perceptron couldn't shatter like that single line, but then that wasn't true for other sets of size 3, so I couldn't say that 3 is a breakpoint, right? So that's the explanation for C. D, show H cannot shatter any set of k points. So I think according to me, this is the correct answer, right? So for the proof, we need to show that H cannot shatter any set of k points, and this is the correct answer. E is showing us something that's like completely opposite to the definition of the growth function. So obviously that's not something that we're looking at here. That's not correct. Okay, so these 4 quiz questions, I'm assuming that everybody will have like a better understanding of what a breakpoint is and what is the relationship between a growth function and the breakpoint, and how whenever we are asking you to prove that k is a breakpoint versus k is not a breakpoint, how should you proceed? So having said that, let's actually start focusing on what we want to in this lecture, which is to find a bound for the growth function. Okay, so the way we are going to begin with that is to look at this example or this puzzle, the combinatorial puzzle that we looked at in the previous lecture. And we looked at 3 points, and then this question was left open. How many dichotomies can you list on 4 points? So here we have like x1, x2, x3, and x4, such that no 2 are shattered. Let's look at this arrangement of like 1, 2, 3, 4, 5 dichotomies, right? And let's look at every pair. So x1 and x2, like we have this negative repeated multiple times. Obviously, this is not shattered. You can go on and check x2 and x3, of course, like a repeat of negative and negative, negative and negative, not shattered. x2 and x4, again, a repeat of negative and negative, not shattered. x3 and x4, again, multiple negatives, so not shattered. So basically, the answer to that question is we have 5 dichotomies. Well, we can also check that by trying to add another dichotomy and see if the 6th one is able to have like no 2 shattered. Is it possible or not? Okay, so let me add a 6th dichotomy that does not exist amongst these 5, which is going to be, let's say, like you can add any one. So this is like the black ones and something like this. Okay, so now if we look at every pair of points, which is like x1 and x2, oh well, there is a repeat here. Yeah, so x1 and x2 is not shattered. Let's look at x2 and x3. So we have a negative, negative. Okay, that's a repeat, that's fine. Negative, positive, positive, negative, and positive, positive. Okay, so here x2 and x3 are shattered, which we don't want, right? So that means the answer to this question is 5 dichotomies. Now the question is, why do we want to do this analysis? What we really want to do is we want to extend this analysis to n points instead of like 4 points here, right? And we want to look at any set of k points such that no subset of like k points is shattered. So what we'll do is we'll extend this analysis to n data points with k subsets and see that those k subsets are not shattered by a dichotomy, and that is going to help us find a bound for the growth function that we are looking at. Okay, so we are going to begin our analysis in the next video, and that's it for this one.